So now we have the exercises of this chapter. The first one is talking about two random variables x and y, which have a density, joint density function 1 over x squared times y squared, and both x and y are greater than or equal to 1, as you can see. Now, the first thing it wants from us is to compute the joint density function of u, which is equal to x times y, and v, which is equal to x over y. Now, we know that this is a Jacobian example, so we're going to have to use the Jacobian, and we're going to find the x and y values in terms of u and v. And then it's asking for the marginals, of course. Now, to find them, to find x and y in terms of u and v, all we have to do is just check those two values. And as you can see, if we multiply u and v together, the y's will, go away, and we will have x squared left over here only. So x is going to be equal to square root of u times v. And for y, we can just replace x with square root of u times v, and then send it to the left side and see that it's u over square root of u times v. And if you simplify more, you will see that y is actually equal to the square root of u over v. Now, for the Jacobian, all we need to do is just take the derivatives of both u and v in terms of x and y. And with, as you can see, let's get there. As you can see, the Jacobian is here. So if you integrate, if you differentiate u in terms of x, you get y, and if you differentiate u in terms of y, you get x. Same for v. If you integrate it in terms of x, then you get 1 over y, and differentiate in terms of x, you get 1 over y, and if you differentiate in terms of y, you get minus x over y squared. And this, then you have to take the, So you can just take the determinant of this matrix, and you will see that it's 2x over y, minus 2x over y. Now, in this Jacobian, we need the 1 over the absolute value of Jacobian. We know that. So the absolute value of this term is actually where the minus sign disappears, because we know that both x and y, they are greater than 1. So they are both positive numbers. So 2x over y is going to be positive as well. So the absolute value of this one is just removing the sign. And you are going to need the 1 over the absolute sign. So you're going to get y over 2x from this Jacobian. Now, we know that x and y are, they can be seen as u times v, square root of u times v for x, and square root of u over v for y. So you just replace x and y with u and v. And at last, in the end, you can see that this, joint density function of u and v can be written as 1 over 2 u squared v. Now, the important part here, the hard part here, is not this calculation, but the calculation of the limits, constraints. Now, we know from the previous page that x is greater than or equal to 1 and y is greater than or equal to 1. We also know that x is equal to square root of uv. So square root of uv should be greater than or equal to 1, which means that uv is going to be greater than or equal to 1, which is one of our limits. And the other one is, we know that y is equal to or greater than 1, which means that square root of u over v is going to be equal to or greater than 1, which means that u should be greater than or equal to v, which is another of our constraints. We also know that u should be greater than 1 because u is x times y, so it's going to be greater than y. And v is going to be, as you can see, it's x over y. Now, v can be 0 and v can be infinity. Why? Because x can take any value from 1 to infinity. Y can take any value from 1 to infinity. Let's assume that x is close to 1 and y is close to infinity. So v is going to be greater than 0, but close to 0. And the other way around, x can go to infinity and y can be a small value, which gives v the ability to go to infinity as well. So v is greater than 0, can go to infinity. On the other hand, u is greater than or equal to 1 over here. So we have 4 different limits. If we just draw them or compare them mathematically, we're going to see that these two are our constraints that are limiting the most. So we can take these two as our limits. So from here, we need to find the marginals because we have already found the joint density function. Now we need the marginal values, marginal density functions. What we need to do is just take the integral of this term with respect to u or with respect to v, whichever margin we are finding. Now, the thing is, for u, to find the margin of u, we need to integrate for v, which is easy. You just integrate from 1 over u to u, because as you can see here, for v, if we left v alone, v is greater than 1 over u and v is less than u. So we have actually a nice set of limits, upper and lower limits for v, which is going to be 1 over u to u. On the other hand, if we want to find the margin of v, we need to take the integration. We have to integrate over u, and when you integrate over u, you have two different limits over here, upper and lower limits over here. The reason for that is, now I will just share something with you, and we will see why that's like this. The reason for that is, let's just share this one. Now, this Desmos calculator helps you create some, shapes and, limits, other stuff with your, just a second, where is the sharing? Yes, okay, screen sharing. Now, I'm gonna just go back and write x instead of u and y instead of v, because x and y is how it's used here. So we know that xy is greater than or equal to 1. And we also know that x is greater than y, greater than or equal to actually y. Now, I have two different, shapes over here, two different limits. As you can see, this one is x is greater than or equal to y, this line here and the shaded area below it. And these two areas, let's just zoom out of it, these two areas are x times y is greater than 1. Now, I also know that u is going to be, a bit greater than, let's say, 1, and v is going to be greater than 0. So this shaded area is my integration area, okay? This area only, not anywhere else, just this area. Because I already know that u, which is x here, is going to be greater than 1 anyway. So when you take a look at here, if you want to integrate for u, you have to, which is x in this drawing, you have to draw lines parallel to x or u. So when you draw lines parallel to x, you can see that there are two different integrals here. In the first one, the arrows are entering the integral area from this shape over this polynomial, and in the second one, they are entering from this line. So I have two different integrals here. And this integral can be, okay, why is the sharing paused though? Yeah, as you can see, there are two different lines here. This one is a polynomial and this line. As I can enter the u, this, when I draw parallels to u, I can enter this area, this shaded area, which is my integral area, from either this part, this, polynomial, or this line. So these are two different integrals, which is going to be shown like this. As you can see, it can be from 1 over v to infinity, which was the shape in the bottom, or from v to infinity, which is the shape on the top, the line on the top. Now, this one is when v is between 1 and 0, and this one happens when v is greater than 1. You can just integrate these two values and put those limits, upper and lower limits, into the integral after you integrate into the solution, and you will get 1 over 2 for the first one and 1 over v squared for the second one. Now, the second exercise. Let x and y be random losses with joint transitive function fxy e to the power of minus x plus y. Now, this is a bit easier. It looks a bit easier. An insurance policy is written to reimburse x plus y. Okay. If there's something wrong with this, let's say item or something else, you're gonna get x plus y. Okay. Calculate the probability that the reimbursement is less than 1. Now, the reimbursement value is x plus y, so it's asking us to find the probability of x plus y being less than or equal to 1. So we just have one, limit, one constant for us. X plus y is less than or equal to 1. I'm just going to use this to integrate this joint density function. Now, it's actually pretty easy because all you have to do is just write the area you're going to take the limit and write the f function, the joint density function, and then start integrating. Now, think about this. You can just let's say draw this one like this. Now, I know that both x and y is greater than 0, so they are over here, somewhere over here, this area. And I also know that x plus y is less than 1, so this line is my limit. So my shaded area, my integral area is this part. Okay, whatever is here, okay, over here. So in this part, I'm gonna have to integrate for x and for y. So if I want to integrate for x, all I have to do is just draw lines parallel to x, which is like this, and I will see that these lines are entering from x is equal to 0 and exiting from 1 minus y, x is equal to 1 minus y. So the integration for x is going to be from 0 to 1 minus y. Integration of y is going to be the smallest value. The lower limit is going to be the smallest value in here, which is 0, and the upper limit is going to be the highest value of y, which is 1. So it's going to be from 0 to 1, and we integrate this, and we're done. This is actually a very easy question. If you understand that you have to find the integral for x plus y is less than 1. Okay. So the next question is, electronic device contains two circuits. The second circuit is a backup for the first and is switched on only when the first circuit has failed. The electronic device goes down when the second circuit fails. So the continuous random variables x and y denote the lifetimes of the first circuit and the second circuit, and have the joint tensor function 24 over x plus y to the power of 4. Now, we have two random variables x and y, and they denote the lifetimes of first and second circuit separately, and the lifetime of the device takes both of them together. So which is x plus y. The lifetime of the device is going to be x plus y, because the second circuit only starts its lifetime after the first one is dead. So x plus y is our total lifetime, and it's asking us the expected value of time. So it's asking us the expected value of x plus y. So to find the expected value of x plus y, all I have to do is integrate this joint function with x plus y as a multiplier, like this. Now we're going to take x and y, they are both greater than 1, so we're going to take x and y limits from 1 to infinity as well. So after you integrate this value, which is not easy, by the way, it's going to take a long time, at least 5, maybe 10 minutes to integrate this one by hand. So you find 6. So x plus y, the expectation of x plus y is 6. So the expected expected lifetime of the device is just 6. It's going to be months, years, we don't know the unit, but still it's 6 units. The thing is, over here, all you have to do is just find that you are looking for the expectation of x plus y and be able to integrate this value. That's all you need to be able to do here. That's it. And then you can find the answer very easily. And in exercise 4, we have two random variables. They are independent and exponentially distributed with parameters 1 and 2. We know their distribution. They're exponential, so the first one, which is x, is distributed with PDF is e to the power of minus x, and the second one, y, has a PDF of 2 times e to the power of minus 2y, which is going to be used here because they're independent. Their joint density functions just multiplication of these two separate and independent density functions. So we're going to find the joint density function by just multiplying these two. We also are looking for the joint density function of x is equal to x plus y and by r is equal to x over x plus y. We need to find the values for x and y. So you can see, if we multiply these two values, s and r values, we're going to find s times r is equal to x. So we have already found x. We also know that s is equal to x plus y, so we can just write these values. So let's see, for example, we know that s times r is x. Just write s times r here. So you're gonna get y is equal to s minus sr. So you can see here. Let's just write it here. We know that s times r is gonna be equal to x, because we know that when we multiply s and r over here, s and r over here, we're gonna get x only. And we also know that if we write like this, sr plus y, we're gonna see that y is equal to s minus sr. We already know x and y in terms of s and r. Then we're gonna have to find the Jacobian as well, because it's a Jacobian question, obviously. So what we need to do is just find the differentiations of x and r in terms of x and y, which is going to give us these values. Then we take the determinants over here, so we get -1 over x plus y, which is going to be -1 over s. Now, we don't know the limit of s yet, but we know that it's x plus y, so it should be positive. And this value is going to be negative with the minus, so we're going to get rid of this minus sign when we take this into absolute value, and we're going to switch the s upwards, because we're going to have to find a 1 over Jacobian, 1 over absolute Jacobian. So it's going to be s. The value we're looking for is going to be s from here. On the other hand, we already know that this is our joint probability, for FSR. We need this one, and we're going to have to multiply this with s, which is going to be sx plus y. This is the joint, this part. Oops, sorry. We have to remove it. This part over here is just a joint probability of x and y, because we just need to multiply them both. This one comes from s, the Jacobian, x plus y. So from here we can just use the x values and y values for s and r and just replace them. X and y, replace x and y with s and r, and we're gonna get this final joint density function for s and r. Now we need to find the limits of s and r as well. Now we know that s is equal to x plus y. Now both x and y are from 0 to infinity, so s is going to be from 0 to infinity as well. On the other hand, r is equal to x over x plus y. Now, x and y are both from 0 to infinity, and we know that x is always less than x plus y. They might be equal if y is equal to 0, but on the other hand, it's almost always going to be smaller than this value. So this division is going to be less than 1. It might be equal to 1 if y is equal to 0, which is not likely, but still it's from 0 to 1. So we're going to write that r is from 0 to 1. This is our limits. These are our limits as well. So what we need from here are the marginals, part B starting now. It wants us to find the marginals. The marginals are going to be found by integrating with respect to the other variables. So for r, to find the margin of r, we need to integrate in terms of s. So s had a limit of 0 to infinity. All I have to do is just write this limit and integrate this value, and I'm going to get this 2 over 2 minus r squared. This is the marginal density function of r. Then I have to find the expected value of r. From this one, we're going to have to find the expected value of r, because it's asking us for the expected value of r. So what we need to do is just multiply this with r and integrated it from 0 to 1, as r is distributed from 0 to 1. So it's 2r over 2 minus r squared dr from 0 to 1. All you have to do is integrate this one, and then you get 1 minus log 2 times 2. So in here, we need to be able to find the limit values to be able to continue the question. If you cannot find these values, which is probably the most important part of here, you cannot continue over here, because you will not be able to take the integral. Okay, you can always write the integral and you say, okay, I cannot find the limits, but this is going to give me, this part is going to give me the expected value. Yeah, you will get partial points from them most probably, but still, if you cannot find these values, you cannot get the latest, the final solution, not the latest, but the final solution. And exercise 5. Now this one is a bit more different from previous questions. We have discrete joint probability here. So we have two teams. They are playing the finals, and whichever team wins 4 matches is going to win the final. And one of the teams is stronger and the other is weaker. And a weaker team has a probability of 0.45 of winning. And then it says, what's the joint probability mass function of the number of games played in the final if we know that the weaker team has won the final. So the final requires any one of the two teams to win 4 matches, which means that the final can end in 4 matches, at least 4 matches, or it can take 7 matches. So 4, 5, 6, or 7. 4 different scenarios are possible. But we also know that the weaker team has won, and its winning probability was 0.45. So it's a conditional probability. We have to write the conditional probability formulation. So to be able to do that, we need to find the joint probability for these two variables, and we know that the weaker team has won, so we need to find the marginal probability of the weaker team winning. Now, if you write these like this, let's assume that x is equal to 0 if the weaker team is the winner, and equal to 1 if the stronger team is the winner. We also know that x is going to be equal to 0, and let y be the number of matches played. So what we are looking for is this part, actually, the joint probability, joint PDF over the marginal, but we start with this one. We start with the top side. This one has the formula, as you can see here. Now, think of this as like this. Think of this part like this. Assume that you have ended the game in 7 matches. So you have won 4 matches out of 7. Okay, cool. Winning 4 matches out of 7 is normally a binomial random variable, There's a success rate, there are a number of trials, so you're winning. But in here, you're actually winning 4 matches, and your last win is ending the game, okay? So your last win is going to be the last success, and it's going to end the game, which will turn this into negative binomial because you have to accumulate successes over here, okay? It's like the geometric variable where you get a success and you're done. In here, you accumulate successes. You keep taking those successes until you find a suitable number of successes, which is 4 here. So the formula you can see here comes from negative binomial random variable. This part here, k minus 1, choose 3. Now, in this k minus 1, choose 3, this picking is, you can just think of this from binomial as well. You have a number of games played, k games played. The last game is a win for sure. You cannot do anything else there, because if you don't win the last game, it wasn't going to be played anyway, because you need to find 4 wins, and the 4th win will end the match and the final. So the last game is a lock-in win for the weak team. So removing the last game, you need to win 3 other matches from k minus 1 games, which can be 6 games if we have won at the 7th game. It can be 3 games if we have won at the 4th game. But it's k minus 1 anyway. So this k minus 1 choose 3 comes from there. And these values are just like binomial random variable. You're going to have to win 4 times, and the other team is going to win k minus 4 times. So this is our joint probability. I'm also looking for the marginal probability of x is equal to 0, which is the sum of all these values for each k value from 4 to 7. So we just put these into the equation, and we get the division of these two values, which is going to give us 4 different values. The PMFs: 0.1 for winning in 4 matches, 0.23 for winning in 5 matches, 0.32 for winning in 6 matches, and 0.35 for winning in 7 matches, which is going to be the PMF of this conditional joint conditional PMF. So the 6th one, we know there's a joint PMF again. We are given that one for x and y in terms of k and m. So k is related to x, m is related to y. And this is the formula. So we know that k starts from 0 and goes to infinity, but m starts from k and goes to infinity. So k is actually related to m, and m is an upper limit for k. So y is an upper limit for x. We can see that from just these two limit values. Find the marginal PMFs of x and y. So we need to find the margins of here. This is a discrete PMF. So what I need to do is just sum on one of the variables to find the margin PMF of the other variables. So we're going to start summing. I'm going to find the margin of x first. So I'm going to start summing on y, which is related to m. So I'll just replace m with y and start summing. As you can see here, we are summing y from x to infinity because the lower limit of y is x. It was given here. Over here, the lower limit of y is x. So I'm starting the summation from x to infinity. And this is what I'm going to sum. Now, as I'm summing over y, I can remove anything else outside. I can just send them outside. So e to the power of minus 2 and x factorial are going outside. So the value that's left here is 1 over y minus x factorial. Now, instead of writing y minus x, I'm going to write k. So if I replace x over here, y minus x is going to be 0. So instead of writing y minus x, when I write k, I'm going to get k is from 0 to infinity, 1 over k factorial, the summation of 1 over k factorial. Now, this should be something we know. This is something we already know. You may not remember it, but this summation is equal to e, the natural number. So I'm just going to write e instead of this summation value, which is going to be simplified by this e to the minus of power of minus 2, which is going to give me e to the minus of e to the power of minus 1. Now, this is the, let's say, marginal PMF of x. Now I need to find the marginal PMF of y, which is going to be found by summing on x. So I'm just going to sum x from 0 to y, the same joint PMF. So from here, I'm just going to remove anything I don't need, which is e to the power of minus 2. This one goes out. Now, I want to find something that resembles something I know, x factorial, y minus x factorial. All I have to do is just add here y factorial, and it's going to be, the binomial summation from 0 to y. So I can see this value, which is the binomial summation from 0 to y, and this is actually equal to 2 to the power of y. This is the number of subsets. You can just find this if you keep digging, but this is actually the number of subsets, which is 2 to the power of y. And I also have these two values over here, so I add them together. I can see that the marginal PDF of y is e to the power of minus 2 times 2 to the power of y over y factorial. Now, these are just the marginal values. What I need is the b for b. Find the joint probability mass function of x and x minus y minus x. Now, I'm getting a new variable here. This is z. Z is equal to y minus x. And are they independent? We'll see. I already know the joint, the margin of x, so I'm just going to keep this over here. And I will start by finding the joint PMF of x and z. Now, as you can see, I have x over here and z over here. Now, y minus x is z. I can just leave y alone. Y is equal to x plus z. Now, this is something I know. X equal to z and y is equal to x plus z. I already know this joint formula over here. So I can just write x instead of k values and y minus x instead of m values, which is going to get this equation. Now, from here, this is my joint PMF. From here, I need to show that my my joint PMF, my variables for this joint PMF are independent. Now, I can show it in two different ways. First is I can say, okay, I can just factor this value into x and z, and you're done. You don't need to do anything else. If you can say that, if you can show that you can factor this into two different sets, which you can, x factorial and z factorial, you can just grab them apart, and they will be two multiplications, so they're going to be factored into two sets. You can just say that this is independent, which you can do that, and you can just say that, oh, I don't know the PMF of X, so I can just divide this one with this one to find the PMF of Z. It's okay. Or you can try to find the PMF of Z, which is a bit harder, but still doable. We know that Z is equal to Y minus X. So I'm just going to find this, PMF value, which is going to give me e to the minus power of minus 1 over Z factorial. Now, what you need to do is just, remove this one, X from this one, and you will get the Z value, marginal PMF of Z. And then we already know this one happened here. So all I have to do is just multiply these two and show that multiplication of these two is equal to this one, which holds. So this one, in this one, X and Z are independent random variables. Now, the last one, the last exercise is a bit easier, but there's a tricky part to it as well, because it says that a fair die is successfully rolled. It's a die question that X and Y denote the spectral number of rolls necessary to obtain a 6 and a 5. Find the expected value of X. Now, the expected value of X denotes the number of times you require to roll a 6. This is geometric. Okay, so the probability of getting a 6 in one roll is 1 over 6. As it's geometric, it's going to be just 6. That's it. And then you have X given Y is equal to 1. This says that Y is equal to 1 says that 5 has come up in the first roll. Okay, and you're still looking for the number of dice rolls you need to get a 6 value, to get 6 to come up, which is again equal to 6. But I have already rolled once, so 1 plus 6, which is equal to 7. And for the last part, for C, we're looking for the probability, expectation of X given Y is equal to 5. So I know that the first time a 5 is seen is in the 5th roll. Okay, so in the first 4 rolls, you cannot have a 5 ever. Then, which means that for the first roll, your chance of getting a 6 is 1 over 5. And then for the second roll, 1 over 5 again. For the third roll, 1 over 5 again. For the fourth roll, 1 over 5 again. So what you need to do is just find the expected values like this. So think about it. If I get 6 in the first roll, I have 1 over 5 of getting it, and I will just get a value of 1. If I get 6 in the second roll, then I have a chance of 4 over 5 of not getting it and 1 over 5 of getting it with 2 steps taken, 2 dice rolls. And for 3, you need to make sure that you don't get any 6 in the first 2 rolls and the 6 in the third roll. So 3 times 4 over 5 to the power of 2 times 1 over 5. In the fourth roll, it's the same. You shouldn't get 6 for the first 3 times, and then you get 6 in the fourth time. Now, why 1 over 5? Because we have removed 5 from the equation. 5 is never there because I know that I didn't roll any 5s, so it's always going to be 1 over 5 and 1 over 5 for these values. But after the 5th roll, okay, I have rolled 5 times yet, and after the 5th roll, I know that it's going to be reset. Everything is going to be reset, and the chance of getting a 6 is 1 over 6. So as it's geometric, the number of dice I need to roll is going to be 6 again. So not getting any 6s in the first 4 rolls is 4 over 5 to the power of 4. And then you get 5 rolls in total, because the 5th roll is a 5 for sure because of the condition. And then you find that you will need to wait in average 6 more times, which is going to give you a total of 5.8 dice rolls, which is like 6 dice rolls like this.